Good afternoon. My name is Wei Hu. Okay, I have one of the shorter names in the conference. I'm based in San Francisco, United States, California. Okay, I'm here to talk to you about scaling for intelligence, how distributed databases, SQL databases work in the age of AI. Right, and let's see now. Okay, so to begin with, modern AI depends on data, right? I mean, that's it, right? And the key thing is that the large language models we have today, like ChatGPT and so forth, they're all trained on public open source data, right? And to make them useful for your applications, you really need to have them work with your business data, right? Because otherwise, they can't really be relevant to the work that you do. Um, and so this is why I say that, good AI really depends on good databases because typically enterprise data is stored in databases and that's where they are, right? And what we see is that agentic AI applications are real time and generate heavy loads on the database because ultimately these are machines, right? Machine driven accesses to databases generate huge loads that humans do not, right? And what's interesting is that AI depends on strong consistency. They want to get the correct answers, right? So inconsistent data can lead to, you know, problems. You confuse the model, right? And stale data is even worse. Now you get, model is outdated. Right? You get the wrong information, right? So the challenge today for database design really is how do you keep up with the demands of AI on your data, right? The high volume, high intensity, and so forth. And this is where distributed database is coming. Now, I want to start with the definition. What is a distributed database? A distributed database is a database that stores its data across multiple physical databases that are in different locations. The different locations can be in different servers in the same data center, different data centers, different availability zones in a cloud, different clouds, different countries, and so forth. Right? And the key is that each location stores a subset of the data, but together they have all the data, right? And the second property is that it is a single logical database. It looks like one database to the application and to administrator. So you have, like in this case, three different pieces. You don't manage three different databases. You manage one, right? All right. And this technology has been evolving over many years. So initially, all the mainstream distributed databases are NoSQL key value stores like Cassandra and so forth, right? Then I think in 2000, early 2000s, Google made a really big discovery, which is the Google Cloud Spanner, which they internally worked on for 2013, 2011, and so forth, and first released in 2017. And interesting enough, the reason they worked on this was they realized that distributed key value NoSQL stores are highly limiting and impose a lot of burden on application developers, right? And so they said it is very difficult to build applications without strong schemas, cross-row transactions, and so forth, right? And that's why they developed this thing. And it runs only in the Google Cloud, right? Then CockroachDB in 2015 sort of cloned them, right? They tried very hard to copy it and to run it in, to remove the dependencies on the Google Cloud and so forth, right? And interestingly enough, this is coming later, it's built upon a distributed key value store called RocksDB, right? And Yugabyte is another thing that came about, which also took a Postgres front end and put it on top of distributed key value store, right? And of course, Oracle, we come in 2017, and what we claim to be is the most full-featured distributed database. And that's important because all databases have limitations and conflicts. And so what Oracle did was that because we started with a very full database engine, we're able to offer a very full set of functionality with distribution. Now, in this talk, I'm going to use the Oracle Globally Distributed AI Database as an example, right? And it's a good example. So because I'm in Greece, so hopefully most of you recognize this picture, right? So this is the Oracle at Delphi, right? The Oracle at Delphi is where you go to ask, what will happen to you in the future, right? And so in some sense, you can use the Oracle AI database as a way to look into the future of databases, right? Because Oracle has the most features, in some sense, you can see where the superset of everything is and where other people are trying to catch up to, right? And I think it's a good way to show where other databases and the industry as a whole is headed. All right. So let me see. So again, a Oracle Global Distributed AI database is a single logical database, right? If data is physically located across different locations and it's called shards, The shards can be in different locations and can be replicated for survivability because you don't want to lose a shard and lose your database, right? So the shards are distributed all over the place. They're replicated such that if one location goes down, your highly redundant survives, right? And all the shards process requests. So it's an active-active architecture. Okay. It's strongly consistent, and that's important because you want to make sure that when you do an update somewhere, everybody sees your updates. You don't get inconsistent results. You don't get you don't get eventual consistency and so forth, right? And that really simplifies life for developers, right? And the data, of course, can be redistributed online because as you add more servers, more storage, you want to move the data around to make sure that the thing is load balanced properly, and that can be done online. Now, I want to just explain some of the use cases, why you want to do this, right? So number one is to create what I call always-on databases. Databases that can survive failures of servers, of storage, of data centers, of regions, and so forth, right? And as we've seen with recent events, this is actually very important. If you're not replicated across different regions, you're in danger, right? Second thing is this concept of data residency, which is that we see countries are requiring data for its citizens to be stored in the country, right? They don't want, data in Japan to be stored in the United States, for instance, right? And also the third one is user proximity, which is that if you're operating a global business, you want the data for your customers in a certain region to be close to the customers in that region, right? So the worst thing to happen is for customers in India have to come to Latin America to fetch this data, right? Because that's just like going to be very, very slow. And of course, the distributed database is a way to glom together lots and lots of servers, and so it's a way to build very large scale for analytics, for AI, as well as OLTP, so we call hyperscale. What I'm going to do now is talk to some actual customer examples. So for instance, for hyperscale, this is an Oracle internal deployment that runs a multi-petabyte scale database, right, that needs very, very fast response time, and this runs on 104 physical servers. Right? And when you aggregate this many servers together, you have like 5,000 CPU cores, 77 terabytes of DRAM memory, and so forth. So these are very massive systems. So the next one is a always-on architecture, which is how a certain financial company, actually a global payments provider, deploys their systems, which is they deploy in 3 different regions across the world. Within each region, there are 3 replicas, right? And it's an active deployment such that every one of these servers are processing requests actively, right? And this architecture, of course, protects against server failures, availability zone failures, regional failures, right? And they can do all this and still get very, very fast failover times. So in their measurements, they're getting like, if a server's down, they can fail over to another server in less than 3 seconds, right? And with 0 data loss. Okay, and that's really good because this is what you need for financial transactions. This one is also an interesting one, which is data sovereignty, because I think people are not as familiar with this, which is that India actually has some of the strictest data sovereignty requirements. So they require the transaction data involving Indian citizens to be stored in India. So this is a major North American bank, and initially they stored all the world's data in the United States, right? So that obviously doesn't work for India anymore. So what they did was they converted this into a distributed database where they stored the India data in India, replicated within India across 2 different data centers. Then the rest of the world, except for India, remains in the United States. And it's also replicated for survivability, right? And the key thing is that because this is a distributed database, the whole thing looks like one logical database to the applications. What this means is that they can keep the application in the United States unchanged while the data is segregated out for each country. Okay? And this is a very important property because the other way to do this was actually to replicate the data tier, the application tier in every single country. Right? Now, for banks, the application tiers are very, very complicated. There are lots of moving pieces in the connection to other applications and so forth. So having to replicate the application tier also is just incredibly expensive and just not feasible for the countries they need to deal with. Right? So this architecture is actually a very cost-effective way to meet the data residency requirements and so forth. So AI, right? So AI brings additional use cases. So we see, first of all, fast semantic searches with vector data, right? Because you have, actually, I'll talk about this a little bit more, right? Of course, you can do semantic searches combined with structured and unstructured data in the database to do interesting stuff, right? We can support agentic workloads that combines private data with large language model trained on public data through RAG and so forth. And of course, model fine-tuning, which is something very interesting that I'll talk about towards the end of this talk. Okay, so I want to talk about performance considerations. And for me, the really key thing is really how do you cheat the speed of light? Because that's really the killer of performance, right? So distributed databases, because I'm putting the data in multiple locations, has some inherent costs, right? So first of all, cross-node communications between servers is going to be more expensive than intra-node operations. So if an operation only occurs within a single server, that's going to be much, much faster than an operation that involves multiple servers communicating over the network, right? And furthermore, the longer the network is, the slower it's going to be because the speed of light takes longer to travel the distance, right? And of course, if you increase the number of network hops, it also adds further latency, right? So to reduce all this inevitable overhead, what we're trying to do is, number one, send as little data over the network as possible. Ideally, send no data over the network, right? Number two, you want to try to keep your data access local, right? Within the single data center or single region where the latency is very, very short, instead of going across region. Thirdly, you want to reduce the number of network round trip calls when you execute queries, right? And if you don't do any of this stuff, your application will still work, but it will be very slow, right? And speed, I think, is actually, latency is actually an important property. So how do you do this? So the way that Oracle does it is that we basically support a whole bunch of what I call data distribution methods, right? And in fact, we support the most of any distributed database out there. And so let me explain what this is. So you have your data in tables, on the left-hand side, right? What we do is we take your tables and we sort of carve the tables up, right? And then we decide that's how we distribute it. And then for each section of the data, we put into a different server. So as you can see on the left-hand side, we have 3 tables, and then we carve the 3 tables up, so we spread them across 3 different physical servers in 3 different geographies, right? So that's what data distribution is called, which is how do I take the data, distribute them across different servers, right? Now, the simplest one, of course, actually, I'll start. So one way to do it is, of course, by list a range of values. So you might say that the top one, you might say, okay, I'll take the primary key, for instance, and I put data with the primary key of the United States, stored in the USA shard. Data that whose primary key is in the European Union, stored in the European Union shard, and so forth. What this does is it localizes your data to the country and region from which it's likely to be accessed. So you can also use ranges and so forth, right? Then system manager, which is basically consistent hash. If you just want to, if you don't care, you just want to evenly spread it out, you can just hash the data, just hash it out, right? And that's good for things like phone numbers and so forth, and particularly within a single country or region. And lastly, we have something called the composite distribution, which is where you have multi-level data distribution. You might have, for instance, at the highest level, countries, right? Or US, European Union, India, and then within each one, then do hashing and so forth. Okay, so these are just examples of ways we can distribute the data. Right? Now, of course, the reason we're doing this is to give you locality, right? So you want to make sure that data accessed from a certain geography is automatically placed in that geography, right? And also eliminate hotspots. And an interesting one that I particularly like to call is something called user-defined distribution. Because generally people think that hashing is good enough. And in fact, most databases, distributed databases only support hashing, right? And hashing is great, except that data is not always evenly distributed. In fact, in real life, a lot of data is skewed, right? So you have hotspots, right? So for example, music is a good example, right? So Taylor Swift is far more popular than 99.99% of the musicians out there, right? So you put Taylor Swift in the same database as everybody else, that database is going to be overloaded. And if you're the person who's co-located with Taylor Swift, you're in deep trouble, right? So what you want to do is really place the hot musicians in their own shards, right? And that's what the user-defined data distribution is. It's a replacement for hashing. It says that I know for my data that these are particularly hot ones, and place these specially for you, right? So what you can do is you can put Taylor Swift her own shard. The Beatles, which are fairly popular too, their own shard, and everybody else put their in the third shard by themselves. And as they become popular and hot, we move them to their own shard out. Okay, so this is a way to really customize the data distribution to meet your application needs. Now, the reason we do all this is, of course, is to make it possible to match where the data is located with the needs of your application. And because every application is different, we support a huge range of data distribution methods to make it efficient for all apps. All right, so that's the first one, data distribution, right? The second one is replication, right? So when you have data, you want to replicate it for availability and so forth, right? So real network, sorry, actually, let me back up. The sad fact is that real world networks are flaky, right? When they work really well. Sometimes they go into a stall state, sometimes they glitch, there are unknown delays and so forth. And so this is why it's important to have multiple ways to replicate your data to match the needs of your networks, right? And so one of the ones that we particularly like is this thing called raft-based replication, right? Raft is sort of like a Paxos-based replication that's sort of like quorum-based, right? And this is what allowed that financial company in the early example to achieve their very fast, 3-second end-to-end failover times, right? And what it is an active-active symmetric configuration where you have an odd number of nodes, right? So in this case, you have 3 nodes in 3 different data centers, all active serving requests, right? And then what happens if one of these nodes shards goes down, the other 2 nodes go into what's called leader election, and then one of them becomes the leader. They now replace the default, the dead node, and it keeps on running. Okay, and this whole process takes place in a few hundred milliseconds, and that's why we can fail over so quickly for the whole database. Right. So this one is actually very good because it gives you automatic single-digit second failovers with 0 data loss, and it maintains strong consistency. Okay, so this is in some senses the one that we recommend for mission-critical applications. Then, of course, as I talked about how networks, sometimes they're flaky, sometimes they're not flaky, with alternative replication methods that can adapt to the characteristics of your networks. So I'm not going to talk about these in detail. All right, then deployment architectures, right? And that's important because you want to have a lot of flexibility in how you actually deploy the shards of your logical database, right? So for example, you can choose each shard independently, right? So I think, you can deploy all the shards, some or all the shards on premises in your own data centers. You can put them in the cloud, right? And in fact, you can put them into multiple clouds, right? And I think that's actually the most interesting case because number one is we've learned over the last 12 months that clouds do fail, right? There's been reported massive outages of certain clouds, not because the servers in them stop running. Their servers running fine, but because of some network and infrastructure issues, you cannot reach the servers, and therefore you cannot get work done, right? So by definition, those clouds have failed. Now, if you're only running on that cloud, your application is down. Your business is stopped, right? But if you're running on multiple clouds, you can actually switch over to a different cloud and continue operation, right? So I think that actually multi-cloud is actually the best resiliency model, either multiple clouds or a combination of cloud and your own data center on premises. And the other interesting about multi-cloud is avoids cloud locking, right? Because you're only dependent on one single cloud. If they raise the prices on you, you're stuck. Whereas if you're running on multiple clouds like this, you can actually shift your data to a different cloud if they decide to raise prices on you, right? And so I think this is actually a very interesting example of what a multi-cloud deployment might look like, but still look like a single logical database of the application. And again, the single logical database is important because that's what allows me to switch clouds and not change the app. Okay. Left unsaid is that ultimately we're doing a distributed SQL database. So the efficiency of how you process SQL is very important, right? And here is something that I think I'm particularly proud of in terms of Oracle, is that Oracle database was designed from day 1, to deliver full SQL in a scale-out cluster. We call them real application clusters, right? And so we basically expanded this to also support distributed scale-out because the initial clusters were all within the single data center, and we basically made it work across multiple data centers, regions, and so forth. And this is very unlike other distributed databases because I think every single distributed database out there started with building a NoSQL engine. Actually, they didn't build it, they just take one. They take an existing NoSQL engine and they try to put SQL on top of it, right? Now, think about it. A NoSQL database is designed not to support SQL, right? The name itself says NoSQL. And you try to put SQL on top of NoSQL, it causes an impedance mismatch and has a lot of issues, right? So we are designed from day one, for SQL, right? And that's why our SQL processing for Oracle is just much better. So this brings up a dirty secret, which is of distributed databases. A distributed database is very powerful, but it has lots of moving parts, right? Lots of servers in lots of data centers, in lots of locations. Managing this can be hard, right? Because managing 12 servers is harder than managing one server. Managing 12 servers in 12 different data centers is going to be harder than managing one server in one data center, right? And so this is where cloud comes in, right? I actually think that distributed database and cloud came in together at the right time, right? So because it's a cloud, you know, it's self-managed. Actually, the Oracle is self-managed, but in any case, it's a managed service, right? So you don't have to worry about management. You can just go to the UI and just click, I want this much processing power in this data center, this much over here, and so forth. And then the whole thing then is created for you and looks like a database, your application, and your app can just connect to it, right? So I think cloud is actually incredibly useful for distributed databases. Right? All right. So going back to vector search and agentic AI, right? So that's the hot thing today, which is how do I combine vector searches with my business data, right? So what happens is the Oracle Global Distributed AI database allows you to basically search on large amounts of vector data, right? So we can basically, actually, let me talk about this differently, which is that vector databases work because of high-speed indexing, right? Because you don't want to search trillions and trillions of rows for data, right? So it's indexing that allows you to find similarity matches. For instance, you can give them a picture and say, find me 10 pictures that are closest to this, right? It doesn't search through all the pictures to find the 10. It goes to an index to find the 10 closest ones. Now, turns out that the highest performance indexes are in memory, right? Now, the problem with in-memory indexes, of course, is that you're limited how much memory you can put into a single physical server, right? And that's what distributed database does for you, which is that I can put together lots and lots of servers and then pool the memory of all these servers to store lots and lots of vector indexes, right? So that's actually the first case, which is that I can just aggregate the memory from all these servers and create a single large pool of vector indexes to do very high-speed vector searches. Right? And so here's some benchmarks that we ran to show this, which is that this is running the Sphere data set, which is a public benchmark, right? Has 1 billion vectors, right? And so what we did was that we basically added more and more servers, right? So you can see that goes from 2 to 8, and you can see that the amount of indexes we can store is just growing linearly, right? So that's okay. But the more interesting part is the blue line in the middle, which shows that the latency does not change, right? Which is that even though I have more and more data, my query latency is still just as fast, right? So that shows you the power of indexing with large data sets, and also just the scaling of the query processing of the distributed stuff. Okay. And so this is what allows us to support petabyte scale analytics and AI, right? Because with AI, modern AI is very, very data dependent. Essentially, the more data your AI has, the smarter it is, right? And so that's just a fact, right? And so basically, by having the ability to build these very, very large vector indexes, I now enable you to search very, very large data sets for similarities and so forth, and make inferences and so forth. And that's just the way to build super intelligence. Okay, model fine-tuning. So this is something which is a surprise to me in some sense, because I didn't believe this actually works when it was first discussed with me, which is the following. Today, as I said before, large language models are trained on open source data. To make it really useful, you have to make it work with your data, right? Without giving all your data away to ChatGPT, OpenAI, and so forth, right? So one way is, of course, prompt engineering, where you can prompt it and you just do a lot of prompting. Okay, that's good. The other one is retrieval augmented generation, which is that I do a vector search of similarity, relevant data, and supply as additional context to a large language model to make queries. That's good. But the third one is called model fine-tuning. If I can take a model and fine-tune it with my data, right, and keep it to myself, then I have a large language model that's out of the box that I don't need to do any of the stuff with, right? Now, the problem with large language models is that, actually, I'm sorry. And fine-tuning, of course, is that, actually, I'm not good. I'm jumping ahead, okay? So the way it works is following. You have an existing model, right? You collect your data, and then you basically train the model on a set of weights based on your existing data. And from those weights, you basically create an adapter, and then you can inject the adapter in a large language model, right? So basically, this process works for models. The biggest problem, of course, is that something like ChatGPT or Gemini are huge models, and you can't get them to train on, right? I mean, that's just not feasible, right? Because very few people have the large GPU farm it takes. But it turns out that if you can take a small model a smaller model that's actually trainable in your own environment, right? But training with your data, in some use cases, it can actually outperform publicly trained large language models, right? Because you think about it this way, ChatGPT that doesn't know anything about your business may not perform as well as a smaller model that actually knows about your business, right? So there's a trade-off line. So there's actually a use case where you can train a small model with your data and actually outperform large language models that are trained only on open source data. So that's the key insight. And that's something that I didn't understand until I just saw the test results and say, aha, this actually works, right? So with the distributed database, what you can do is you can basically do all this training in parallel because your data is spread across multiple shards. You can just in parallel, just feed the data into the pipeline, train the model, eventually merge, and then create your fine-tuned model. Okay, so that's actually the interesting case, use case for this technology that I hadn't expected when we first started doing this. Frankly, I thought it was a bad idea when we first started. Okay, but I was proven wrong. So. And so for this concept, this is called federated fine-tuning, which is that you do in parallel across all these nodes in the distributed database, and you merge them together, right? And of course, why it's good? Number one is compliance, because now your sensitive data is kept only within yourselves. You never send it over the network. You don't send it to any large language model, even as context or whatever, right? And of course, second thing is distributed processing. So it's done massively in parallel, so it's very fast, right? And thirdly, because you're training the data, fine-tuning it, you actually get better inference accuracy than fine-tuned models. Okay, so I want to switch back a little bit and talk about applications in general, which is that you know modern apps require multiple data technologies. Right? So for instance, when I do a food shopping application, it has pictures, has menus, has JSON, has text user reviews, have maps, and so forth, right? And of course now it has AI in it too. So apps typically use multiple data types, and you can do lots of things with them, right? And so that's why you have new types of data. You have relational data, you have documents, you have spatial, you have new types of analytics, right? SQL, machine learning, AI, graph, new workload types, AI vector searches, IoT, blockchain, and so forth, right? So it's very clear that modern apps just use lots of these things in combination. Now, one approach, of course, is to say for each of these special use cases, use a dedicated database, right? So you can say that, okay, for relational, I use Postgres. For documents, I use MongoDB. For spatial, I use PostgreSQL. I use Spark for machine learning, Neo4j for graph, and so forth. So you can see that you can just scale this out, right? And it gets very complicated, right? So now, this is not a very scalable solution because for every use case, now every single app needs to use multiple databases, right? And you can imagine for that banking example I gave you where I need to do data sovereignty, if I use multiple databases in one location, I have to use multiple databases in every other location also, right? So this problem just explodes as you have replication in place. And guess what? Who handles complexity? You do. Right, the developer and IT had to handle it because the database didn't handle it, right? So what we proposed instead was the Oracle technology is this concept of a converged database architecture, right? A converged database architecture basically is a single database that can handle all the data types, right? Relational, non-relational, graph, vector, JSON, machine learning, blockchain, and so forth, right? In one database, right? And so what's nice now, you can just use everything in a single database, and they're all consistent because they work on the same database engine, which means same consistency model, same scalability model, and same availability, right? When you create replication of one, everything is replicated, right? And I use the analogy, it's like the smartphone of data, right? In the early days, I'm trying to how early? Before the iPhone, how's that? Before the iPhone came around, I remember I had a separate digital camera. I had a PDA for my notepad. I had an MP3 player. God, what else? I had an analog cell phone, a Nokia cell phone. So I was carrying 4 different devices, right? So that's what single-purpose databases are like, right? Today, I just have my iPhone. It does everything, right? And furthermore, they all work better together. For my app, I can call a map. I can do everything together, right? So this is what I think is going on, was that all these individual dedicated database technologies, they're all going to converge into a single thing like Oracle. And I think that's where Oracle is, and I think that's where everybody else is headed. Right? Let's see now what else. Okay, actually, I have 10 minutes. Super. So my key takeaways are number one is that I want to draw back to Oracle, right? Uh, so I think first we support more data distribution methods, right? And I explain the reason why. That is really to make it possible for you to place data control the placement of data optimally to meet the needs of your applications. That's it, right? To defeat the speed of light limitations, right? It supports the most replication methods of any distributed database. And again, it is to deal with the realities of real world networks, which are, you know, not always great, right? It's built on a proven relational engine, right? Because we initially used scale out, then we made it work with distributed scale out instead of trying to graph code on top of a NoSQL engine. It has a very broad deployment flexibility, right? So unlike, for instance, like Google, which only deployed available on the Google Cloud, you can deploy it on premises, in a cloud of your choice, or multi-cloud, which I think is the most interesting case, right? And of course, we have a managed cloud service to handle the inevitable complexity, just having lots of these different moving parts, right? And of course, it's built upon the Oracle database, which means you can get a lot of things you expect from a production capability. And of course, it's strongly consistent and it's single logical database. Okay. Okay. So one of the things is that the reason I come out to the Devoxx Greece is really to meet the developers, right? But if you have a chance to meet us also, I welcome you to join us in Las Vegas, because in Las Vegas, we have our annual conference in October, right? What's interesting is we have users of our technology talk about their experience, right? Now, I couldn't bring them here, so I thought I'd just bring one of their presentations here. So this is a slide presentation from PayPal. So PayPal was at Las Vegas, and they talked about how they use, our distributed database to improve availability. And in their case, they deployed it across 3 different regions on the Google Cloud, right? And they talk about how they deploy across 3 AZs for really high resiliency with RTO of 3 seconds. So they can fail with 0 data loss in less than 3 seconds. They like the fact that 0 downtime patching, seamless for upgrades, schema changes, and application upgrades. So I think it's really cool. Okay. And they talk about why they like it. They like it because they require 0 code changes for their apps that are using this. It's always available, which is a critical part, because if they're transferring money, you want to be available, right? And of course, compliance with data residency requirements and centralized management, because it's one logical database, the fact that it scales linearly, and a serverless operation. Okay, so I think that they really summarize, why they do this. Okay, let's see, and I think it's interesting. So I have some resources here, right? So the left is just the description of what the global distributed AI database is. Second one is documentation. The third one is actually the most interesting part, which is the live labs, right? The live labs is a series of examples that you can actually go through and work and run in a sandbox to actually experience capabilities of this technology, right? And then there's a free version of this thing, as well as containerized version, Docker image that you can, Podman image now, okay, that you can actually use to try this thing out. Okay, let me see what else I have here. Okay, and I think that basically what I'm trying to say is that, try this out. This is actually a great technology, and I think that it is in your future, and it will help make you be more effective to be able to do this kind of stuff. Okay. All right, thank you. So this is Oracle for Oracle in Delphi. Okay, thank you. Okay. All right. I think actually, I think instead of taking questions about, sure, please go ahead. Um, uh, Oh, okay. So I think you're saying that the database is just a distribution part. The application needs to be distributed also, right? So number one is absolutely the application should be in multiple locations, because if your app is only one location, if that location goes away, just because data is available elsewhere is not good. But actually, having data available elsewhere is actually not bad either, because at least your data is there. You can always spin up a new application server and continue operation. And in fact, some customers do that, right? But I think the ideal case would have applications running everywhere so that you can just continue operation, right? So, but the key is that, remember, this is a single logical database. So your application anywhere, just connect to the logical endpoint. And then we internally dispatch you to the correct location, right? So this gets more and more complicated. We're talking about not just geographical distribution, but also logical distribution. So I might have to run on different sites. No, you don't. You're running in one place, right? I'm running, but the latency gets high, right? Right. What you do is the key is that how the data is distributed is sort of invisible to you, right? Because you declare when you create the data, this create table statement, and it just says create this thing over there, right? And so you just access it wherever as you do, and we'll get the data to you wherever it is, right? So what usually happens is that customers will deploy the app tiers with the data tiers, right? So like I will have an app tier in Europe, app tier in the United States, and so forth. And if the data is distributed properly, you just happen naturally, you will get to the right place. Right? I mean, that's it. Okay. Now, so for example, when I talk about I separated by Europe, then second level by something else, that's exactly for that use case. Right. So now of course, if you're in Europe, you can still access data in Asia and United States. You just take longer. But European data will be very fast for you, right? So you try to localize access wherever possible, right? You can't be fast 100% of the time because some parts of the world will be farther from you. But the way data distribution works is that it makes sure that most of your access is fast. And the logic of which one is faster stays within the state, right? It's automatically handled. Yes, it is automatic handle. It's part of what I call application design, which is because you know where your data is, right? So you basically tell us. In some cases, it's obvious because for that bank, they have a column which is a country, right? So you know that India data tends to be more accessed in India, right? And so that's a very strong hint. Say, hey, put India data in India, right? So okay, you're welcome. Yes.
The microphone is here, so
okay, microphone is here. Oh, sorry.
I speak or
please go ahead.
Yeah, you mentioned at one point that you can replace certain open source technologies that create fragmentation in in what technologies basically you use, and you can just use Oracle. I mean, I would like to defend Postgres at this point because we are using for 25 years. You mentioned Postgres, then PostGIS, which is the same thing, right? Then JSON. Postgres was the first database to natively support JSON, JSONB.
I think MongoDB.
You think MongoDB, but MongoDB is a toy, right?
Okay. MongoDB is fine. I'm fine with that.
If we speak about serious databases, Postgres has native JSON support.
Okay.
You don't need to use Kafka for the majority of cases unless you are over 100
So is your
terabyte.
question?
I beg your pardon?
So you have a question?
And my question is that you can do this. So basically, all those squares in the screen was Postgres, right?
Actually, there's a difference.
Why should I move away and go to Oracle?
Right. That's a great question. There's two aspects to a converged database. One is multi-model, which is used for multiple data types in a single database. And I think everybody's moving to that direction. If you look at Google's big announcements about LOIDB, they're moving multi-model, right? What they don't typically do is multiple workloads, right? You have multiple workloads, which means you support multiple model types. You can do data warehousing, OLTP, analytics on the same database. And I don't see that happening, right? Because Oracle is saying to no one that's able to do that. Because for instance, even with Postgres, if you look at what Amazon does with Postgres, right? They have Aurora for OLTP, they have Redshift for data warehousing, right? And I see that, right? And so yeah. So anyway, so I think there's two aspects. One is multi-model, which everybody seems to be doing, right? And of course, you can argue about which one does it better, right? But also, there's also multi-workload, which I think is also important, right? Because again, when I add AI, that's a new workload type, right? I want to be able to do work with all my data, and I want to be analyzing my same data with whatever analytic technologies are available to me today, instead of fragmenting my data, moving things around, and so forth. Okay, so that's the difference. Okay, then I think somebody here had the microphone before.
What is an autonomous AI database?
Autonomous AI database is the latest version of the Oracle database that has built-in AI functionality for both vector search as well as agentic applications, right? And yeah, so it's just that's our current technology. It came out in January of this year. Okay, and there's huge announcements about it, right? It's just see, every few years we went through this major architecture, right, to incorporate new technologies, and AI is one of those big things where we just had a massive rethink about how we do things to support it and so forth. So yes, that's the AI database, and autonomous AI database is our cloud version, because our cloud version runs autonomous technologies actually our autonomous database uses the old style machine learning technology, pre large language model to manage itself, but that's how we offer the cloud service. So there's the AI database and autonomous AI database. Okay, I think. Go ahead. Well, maybe you first and the second there.
You mentioned locality in relation to regulations. You gave an example about India. But is there any enforcement at a database level to the access to the data? For example, data may be stored in Greece for Greece, but it can be accessed or written remotely. Is there any limitation on that? And
yes, actually, that's a great question too, which is that we offer very fine-grained access control, right? So you can say that this data, this cell, can only be accessed from certain locations by certain people, right? So we can do that. But it turns out for India, you don't have to do that, because India just says the data has to be stored there, but you can process it elsewhere, because for 24 hours, to be really technical, right? And the reason that is because otherwise it's very hard to move money around, because at some point you need to have a common point, right? So you can look at the data, you can use the data, but it has to be stored physically in India, right? Okay. Because otherwise you can't use it. So it's just like, what's a good example is China. China has very strong data residency requirements, right? So if you run iPhone, your iCloud data in China is stored in China. Right? But I can take my iPhone from China, come to the United States, come to Greece, and look at my data. That's allowed, right? But the data is still stored in China, but I'm looking at it here, right? So you can use the data elsewhere, because you need that to run your operations, but the data needs to be physically stored there. And the data being physically stored there means that the government there can, cut off access to the data, erase it, whatever do. So that's also the regulations that we deal with.
But that means your data is very slow to.
Sorry, there's a question there, and then I'll come back to you. Yes.
Hi, I want to ask, what's the biggest lie or misconception that engineers still believe today about distributed systems, as you were mentioning?
What is the biggest one?
Misconception or a lie that still engineers believe that today about distributed systems?
I think it's hard to say, because the old mantra was that to be a distributed database, you need to run NoSQL. So that has gone, right? Because we've proven that you can do it for it, right? Then the next one was to be a distributed database, you need to run with specialized hardware, right? That's what Google's premise was. I think that's gone, right? Then the third one was, well, to be a distributed database, I have to restrict the functionality severely, right? And so forth. And I think that's mostly gone, because there are still some limitations. So it's an evolving thing, right? There are still some things that a distributed database is going to be harder than a single database to do, primarily around the latency, speed of light, how do you manage it, and so forth. That's where, because again, real networks are real networks. Speed of light is the speed of light, right? We can do things well, but again, if your data is not distributed well or cannot be distributed well, then it's not going to work well. Because just imagine if your data is equally far from you, then you're always paying network latency for some of your access, right? But again, one of the things that we've learned is that for some mission critical applications, latency is actually not that important as durability. right? You want to make sure that no matter what happens to your region, like a drone hits your data center, your data is safe somewhere else, right? So, you know, it's okay, right? So anyway, so I think you had a question in the front.
It wasn't a question.
Oh, okay. That's good.
Actually, a joke that maybe if your data is stored in China and you are here and you have to access it from China, it will be rather slow.
Yes, it would be. It would, but it seems to work, right? Because you know, it's just like people in China were accessing the data in the United States before, right? Because before iPhone data was stored in the United States, and everybody in China, which is the second biggest market for iPhones, I think, it's either second or first biggest. They're all accessing that data in the United States. So some things are amazingly not that latency sensitive. Some things are, right? You know, high-speed banking transactions are, but some things like looking at pictures, text, and so forth, because we're operating at human speed, right? Human speed is like, okay, it's like.
Thank you.
Great, thank you.